Continue key points. We were talking about detecting these key points, and the first case we will consider is we'll consider the corners as key points. Okay. So we went through the simple example where we have the same object in two different images, and there were like two different properties in these two images. First of all, there was a rotation. The objects are at different angle, and the second was scale. So this object is smaller as compared to this particular object. And then the idea was, if we detect key points, they should be consistent between these two images, which will help us in like performing matching of these images. Or first, so that will start with matching of key points, and if key points are matching, then the image will also match. Okay, so as I said, the first algorithm we're going to talk about is corner detection, and we assume that the corners are actually interesting points in images. I think there's a question from Daniel. When we talked about filtering, is there a reason we didn't mention morphological operations, or is that a later topic? So morphological operations, we are not going to cover in this course. So if you will go through like the lecture content, right? So we don't have this topic. Okay, great. Okay, so the idea is we want to detect corners, and we want to detect these corners like using windows. And what we will do is we will try to shift this window throughout the image as we were doing for a filtering. In filtering as well, when we have a kernel, so that acts like a window, and we use that kernel throughout the image to actually identify some set of features or some kind of patterns. So the idea is almost similar. So let's see how it's going to work. So let's say this is your image patch. All right, and this is your small window. So this window will play the role of a kernel, and then this window will try to figure out whether in this particular location whether a corner is present or not. And if it's present, then you're kind of localizing where the corner is present. And if you detect like corners in the whole image, that will also give you like a high level idea about what kind of shape is present in this image. Okay, so we look at small windows. Now the idea is, the basic idea, and this is quite intuitive. So what we do is, let's say we have an image patch in this case here, and in this case it's just binary image, it's black and white. So there are like a couple of rules. So what we do is we take the window and we just try to move that window in the vicinity, in the neighborhood. All right, so in this case we can move it in like any direction. So we can like go this way, the arrow, the direction of the arrow, we can go to the top. And then what we do is we try to monitor if the intensity of the patch which is inside this window, is it changing or not? All right, so the intensity is, if it's a grayscale image, that pixel value, right? So that's the intensity. In this case, like if it's black and white, then you know that this white is like high intensity, black is low intensity. So the intensity you can consider like also average intensity inside the window. You can just sum up the intensities of all the pixels inside the window and just take average. So if you're moving around this window and the intensity is not changing, which means that you are actually on a flat region. All right, so it's not going to change. And you can actually visualize it here. If I move this window maybe slightly towards top or bottom, the intensity is actually not changing, right? It's all black. It doesn't matter like where you move. And if the intensity of all the pixels it's not changing, it means the average intensity will also not change. So if it's not changing, it's a flat region. All right, so if it's an edge, so in this case this is an edge, right? So you are going from very high intensity to very low intensity, and which is causing this edge over here. Now what will happen is, if you have this window in like a region where you have an edge, and if you move this window in the direction of the edge, then the intensity will never change. So if you look at this window and you slightly move it towards the top direction and the bottom direction, so the number of light pixels and the number of dark pixels, they are not changing. And that's why the intensity is not going to change. But if you change, if you change the window's position, maybe in some other direction, which is not the direction of this of this edge, which is like towards left or towards right, then the intensity is going to change. So if you move the window towards left, then the lighter pixels are increasing, which means the intensity will increase. And if you go towards right, the number of darker pixels are increasing, which means intensity is going to go down. So which means that if you move this window in certain direction, in this case, it's like the direction of the edge, the intensity is not changing, but in certain directions it's changing. So that you can consider, it's kind of, it's not a flat region, but it could be an edge. So which means that in some directions it's changing, in some directions it's not. But what if you have a corner? So this is the special case, and this is like something which we are interested in. We don't care about flat regions because these are not interest points and these are not corners. And again, edge, it's not a corner, right? And it's not a flat region as well. So these two are not of interest. But if you look at the corner, and it doesn't matter which direction you shift your window, your intensity will always change. Okay, so that's the basic idea. If you move around your kernel or your window and you are observing some kind of change or change in the behavior or change in the intensity, it means that you can assume that it could be a corner at that location. Okay, we'll use this intuition to detect these corners. All right, so question from Zubin: how can we differentiate between a curve and a corner? So corner is like where more than two edges are meeting, right? So in this case, you can see that. So okay, so now understand. So you are saying that this could be a curve as well. So yeah, don't go into that final level detail, and try to understand it like from an abstract point of view where edges are meeting. So that could be a corner. It doesn't have to be like a perfect intersection. Even if there is a small curve, it is fine. Okay, so the idea is, if you want to differentiate between curve and corner, the only way to do that is if you're using different size for this window. Okay, so if you have a very big size such as this, then this curve could be a corner. But if you try to reduce the size of the window, let's say very small, then this curve could become an edge as well. So it depends upon like what's your window size. Okay, so that's good. Now, question from Shang Yang. Do we have a specific definition for corner? Yeah, so as I said, like if more than two edges are meeting at a point, so that will be your corner. Okay. Now, this might have like remind you of when we're trying to do pattern matching, right? Or we're trying to use filters to detect some kind of patterns in your input image, and that was filtering. So we can do something similar. And the first thing we can do is just perform template matching. So for template matching, what we can do is we can create templates or kernels where we have corners. So this is like one nice example, and you can see here that all these are negative numbers, and over here we have positive numbers. So this kernel is representing a corner. Okay, so these two edges are meeting at this point. So this could be a very nice template to detect corners. And similarly, so this will detect a corner which has this orientation, but you might have the corner in different orientations as well. So then what you can do is you can define like more templates for corners. So this is another one, and this you can see is like is at an angle, so 45 degrees, but still this is a corner. So you have this edge meeting with this edge. So all these are negative numbers. And then what you can do is you can just rotate this kernel, and that will give you like many other kernels which you can use to detect corners at other orientations. And similarly, you can rotate this particular kernel to detect those kind of corners which are at an angle or at a different angle. So you can get like 8 different templates if you just rotate like these by a step of 90 degrees. So that's fine. So another interesting detail you might have noticed is if you just sum up all these values, it will give you a 0, right? Because these are like 5 4s and these are 4 5s, so both are equal to 20, so they will cancel out each other. And this is also like what you do, you normalize your kernel, but this is like, this has a additional spatial meaning, it's 0. So what will happen is if you have different intensities, right, the change in intensity is different, so you want similar behavior. So you want the sum to be 0 when you found this particular pattern, because if these are not summing up to 0, then you might get different numbers for like different kind of corners depending upon what's the intensity of your image. So just to make sure that you always get a 0 for like varying kind of intensities, we just try to normalize that. Okay, question from Sir: does magnitude matter in this filter or only the sign of the number? Magnitude, it will matter because we are trying to normalize it, right? So this number does matter, but overall you will see like all of this is summing up to 0. Was that your question, Sarath?
I mean to ask if I can take -1, -1, -1, and +1, +1, +1 to represent the corners.
Yeah, but then that won't be normalized, right? If you sum all those up, so this is going to give you -5, and this is going to give you just 4, so that will be -0. So then when you have a match, it might give you -0 instead of 0, right? So in this case, we are just ensuring that we will get a perfect 0, which means like the kernel is matching with the corner.
Okay, so any filter where the summation is 0, it works, right?
No, not any filter. I mean, it has a
pattern like this.
Yeah, right. Yeah, it should have this pattern, like pattern of this corner.
Yeah. Okay.
Okay. Fernando's question: do you mean -1? Yeah, if you use just 1 instead of 4 and 5, that will give you -1. Was that your question, Fernando? But we want 0, right, for a perfect match. Okay. Right. Sorry. Just slip of tongue. So that should be -1. Right. That's correct. Okay. So this is template matching, and of course you can do this. But if you think about this, when we are doing filtering, then you can use filtering operation to do a similar template matching as well, right? And let's quickly go over correlation. So in that case, you have your function, and then you have your kernel. You just do element simplification. That's what we are doing. So we try to use this correlation for detecting corners, but the interesting fact here is that in this case we are finding correlation between image and the kernel, right? But what we are going to do here is we are going to find the correlation between the image with itself, and that's called autocorrelation. So we don't have a filter and a kernel, sorry, we don't have a filter or an image patch, we just have the image, and we try to find the correlation with itself. So that's called autocorrelation. And what we do, so this is a simple equation, very easy to follow. So this is trying to find the autocorrelation. So we have this window, which is again like a replacement for that filter. So this is like the region where we will look into, where we'll do the computations, where we will find the correlation. And this is exactly this is the operation which we are going to perform. Now if you look carefully, I is the image, right? And X, if XY is like any particular location for which we are computing the autocorrelation. So this IXY is going to give you the intensity of that pixel. All right. And this first term over here, again, this is going to give you intensity, but this is not the current pixel. This is like the neighborhood of that pixel, because you are shifting the window with U and V, and this UV is like the neighborhood of that particular pixel. So essentially what this is trying to do is you're just looking at a pixel and trying to find out if the intensity at that particular pixel is similar to neighboring pixels or not. So that's like a high level idea of finding autocorrelation. So if you think deeper, then what's going to happen is, if we have a very flat region, right? We saw earlier flat region, the intensity was not changing when we were using a kernel. So if you will have a very flat region, then what will happen is, if you pick a pixel, then that pixel will be exactly same as the neighboring pixels, right? So whichever pixel you try to compare it with, it will be exactly similar. Then this term is going to give you 0, because all the pixels are almost similar. And then which means that you have a very low value, it will be close to 0, and which means that the neighboring pixels are almost similar. Okay, so that will give you like a flat region. I think there is a question from Moment. So it is correlation of an image with its shifted version. Yeah, that's correct, Moment. So not exactly shifted version, because you're considering a pixel and then computing its similarity with its neighborhood. Okay, so it's not like just one shifted version. You are shifting like in all the neighborhood, like which is like close to that pixel, and like how far you look into this window is going to define. Okay, essentially you can look like the look over the whole image. Okay, so that's good. Question from Zubin. It's essentially calculating change in intensity with neighboring pixels. Yeah, that's correct, Zubin. You're just looking for change in intensity. Okay, so that's the intensity, that's the shifted intensity, and this is the window function. This will define like what's the neighborhood you're going to consider. And question from Amir. Ix gives the intensity of image at X. Sorry, the window was okay. Ix gives the intensity of image at X, then what is WXY? Yeah, so WXY is the window. So Zubin, yeah, I mean it's a weight, and that's true, but it's also it's trying to define the boundary which you should not cross when you're computing the autocorrelation. All right, so let me actually, I think it should be there. Yeah, so this is a window function, and it as I said, it will define the boundary. So what's going to happen is, if you are inside the boundary, that the weight will be 1. So that's what Zubin said, like it will act as a weight. And if it's outside the boundary, it will be 0. So it's a very simple step function which will act as a window. So essentially what will happen is, if you try to compute this difference outside this boundary, you're just going to ignore it. So you're only considering pixels inside that window. And of course, I mean, you don't have to use a step function, you can use a Gaussian as well, which means that you are essentially giving more weightage to like close by pixels and less weightage to far away pixels. Okay, so this is fine. We covered this equation, and so yeah, as we discussed, this is like just change in appearance or change in intensity. And this is just giving you one example, like if you compute the autocorrelation at this location, it's kind of giving you a very low value, because it's kind of most of the pixels are brighter. And similarly, you compute maybe for some other location, so then you'll have to consider this window, right? So whenever you compute like this autocorrelation for a pixel value, your window should be centered around that particular pixel. Now let's see how we can use this autocorrelation for corner detection. I have already given you the intuition that if it's a flat region, then it's going to give you 0. And if it's giving you a non-zero value, which is actually very high, a large magnitude, it means that your pixel intensity is actually changing in your neighborhood, right? And that's exactly what we are looking for. So let's try to consider 3 different cases in this image, and I'm not sure if it's visible or not. So we have 3 cross marks. The first one is over here on the clouds. The second one is like on the roof, and the third is over here on the ground. Right. So even before looking at the equations, if we just observe this image, you can see here that we don't have a corner here, right? It's a flat region. And if you look at this, we again don't have a corner, it's just an edge, like edge of the roof. And this region most probably will have an edge because these are leaves right on the ground. So we should have corners here. And so now let's try to visualize what kind of values we will get for autocorrelation if we take patches from these regions. So for this particular location, we are okay, not this location. So this is one patch, and this is a response from like one of these crosses. Okay, if you try to visualize this like as a surface, so this is low intensity, this is high intensity. So you will get something like this. Okay, so this high intensity is corresponding to these pixels. This downward peaks, this is corresponding to this darker pixel over here. Okay, similarly, another patch is giving you autocorrelation of this type of this type of map. And again, you can try to visualize this. That's the third one. You're getting this. Okay, so if it's an edge, then you can see like you will get something like this, because you are getting a very low response. Or you can also say that if you think about sliding your window, then the change in intensity is almost 0 when you are moving in this direction. So this corresponds to the direction of the edge. So then we can say that, okay, this patch is actually corresponding to this roof over here. Okay, so if you compute autocorrelation for this location, you will get something like this. And this one is coming from the clouds. And in this case, again, if you find the correlation, the pixel intensity is not changing a lot, right? It's almost similar. So that's why like very low values. And in this particular case, you can see that we have a peak, or you can say like a negative peak. And this might be coming from this location where we have a lot of like very irregular shapes, right? The intensity is changing a lot. So this is the corner, and this is something which we are interested in. So if you look at this curve, and if you try to correlate this with like filters which we have been using for filtering operation, so this is kind of a surface which we can approximate to a function. Okay, so I will come to that in a while. Now, so that is fine. You can find like these kind of minimas, and if you have a minima, then that those will be your corners. Now let's see like what's the issue with this. So this equation is fine, and we have seen like some of the visualizations, it gives reasonable result. But the issue is, if you think about this, for each pixel location, the amount of computations or the amount of calculations you have to perform, it will be huge, because for each pixel you are looking at the neighborhood. And so if you just do the computation, so your window width, and this is like the shift, and this is the image width. Okay, so if you're using 11 cross 11 kernel and your image size is 600, so it means like 600 cross 600 image. So this means like the number of operations you have in this equation, that's roughly 5 billion, which is a lot. All right, so now the question is, if you want to do this like in real time, or maybe at a fast pace, it will be very challenging. So we don't exactly compute these numbers, but what we do is we try to approximate this using image derivatives. All right, and this is a bit complicated because this requires a lot of mathematical background. We are not going to talk about that. We are not going to do any derivations. I will just give you the equations. Okay, so the basic idea is, this is the pattern which we're looking for if we have corners. Okay, so we approximate this kind of pattern with, let's say, this curve. It could be a Gaussian or something, right? So we try to find this kind of pattern in our autocorrelation, the output of the autocorrelation. So probably I think I should, or maybe just go through this. So what we try to do is we try to approximate. So this Taylor series, you all should know. I don't know like what your background is, but I think you should know what a Taylor series is. So this is like a series which you can use to approximate any function f, right? And if you want to find, if computing the function is very complicated, what you do is you try to approximate it and you try to get rid of like some of the terms over here. Okay, so this is exactly what this curve is trying to show you. So if you have a function, let's say exponent of e, which is the blue curve over here, and this value of n over here, it's showing you like how many terms you are going to use in this Taylor series. So you can see that when you're not using any term, it's kind of a straight line, right? And if you use the first term, you will get again, it's fa, right? Again, it's going to be a straight line with some kind of slope. But as you increase the number of terms, then the approximation is actually getting closer and closer to your actual exponential function. So this series can be used as an approximation. And again, we are going to do the same thing. We are going to approximate this function, and we are going to use like the second order approximation. So again, I'm not going into a lot of details because that will be too time consuming. So don't worry about it if it's not clear. I'll just give you the equations and give you the intuition what exactly is being done there. Okay, so it's a quadratic approximation, and we can approximate this autocorrelation using these terms. So this M is over here is called second moment matrix. And again, you have these vectors here. So this all these terms might be like they are familiar to you, right? So this W is your window function, and these Ix, Iy, these are the partial image derivatives, and that is where it becomes interesting. So I understand like how we come up with this equation, we are not going to cover, and again that will take a lot of time. So but if we just look at this equation, this is pretty interesting, because to compute this M, you just have to compute derivatives of your image, all right, and just use the window function. Now the interesting thing about this is you have to compute the derivative just once, which means that for each location, you're not going to compute the derivative again and again. You can just reuse that derivative, which you have computed just once. So that makes this more faster. Okay, so then if you look at this, let's say this is your original image patch, all right, then you know that your partial derivative in x direction is going to give you edges in maybe a y direction, all right, and this you have done in your programming assignment as well. Then this is the ix term here, this is the iy, the second term over here. This is again the partial derivative in y direction. This is going to give you all the horizontal edges, all right. And then again, what else we have? So once we have these two derivatives, so that's the only mathematical operation we have to perform. Then you can just put like these values over here, and you can get this moment matrix. Now, again, this is fine. You can just multiply these two, so that's going to give you ix, iy. And again, you can just multiply with itself as well, so that will give you ix square and iy square. Okay, so these are the steps for Harris corner detection. Again, we are not going to implement this like in any of the programming assignment, but you should know the steps. This might come in like in your midterm. So the first step is you just compute the M matrix, okay, for each window. So M matrix, as I showed, this is your M matrix. Now this WXY is a window function, and which can be a step function or any weighted function like a Gaussian or something. And this is interesting. This is like your using your derivatives. And as I said, like xy might change, but these derivatives are not going to change, so you can reuse them. Okay, so that's the first step. Then we will compute like a value for each location, which is called the corner response. And again, this is based on some heuristics, so I'm just going to give you the equations. We are not going to go into detail like how we come up with that function. So then we have a function which will give you whether this particular pixel is corner or not. And again, this is based on like what kind of response you are getting from your movement matrix. All right, and then the final step is just non-maximal suppression, because at each pixel location or in the vicinity in the neighborhood, you will have just one corner, right? You can't have like a lot of corners in the same region. Then that's not a corner. So for that, we need a non-maximal suppression, and this is similar to like you did for your edge detection. So let's quickly go through like all these steps which are required for Harris corner detection. You have the input image, all right? And we want to compute this movement matrix for each pixel. So what we do is we first compute the partial derivatives, ix and iy. So I mean, it's optional, you want to blur, so that will that might improve the performance, because if you have a noisy image, then that noise can be omitted. But again, that's optional. So you compute the partial derivatives. So for the components of m, I mean, you have to compute ix square, iy square, and then you multiply ixy. So again, you can just use this. You get these matrices. Now you'll have to perform a Gaussian smoothing on these maps. And for computing the cornerness, as I said, like we just use this equation, and this is kind of giving you the magnitude value. And this is the equation. Again, this is just using Gaussian filtering. So all these terms are like were derived in the third step over here. All right. And you can see here that if you just use the determinant and trace, it's clearly indicating like where the corners are present. All right. And these two are simple steps. You just pick a threshold on C, right, the cornerness, and then you can disregard like some of the corners, and you will filter out like the weak corners, like you used to filter out weak edges, and again non-maximal suppression to just take the peak, and that is going to give you the corners. All right, so these are the steps, and as I said again, I mean, there is a lot of mathematics involved, and we won't have time to like go into detail. So but yeah, so you understand the basic idea, like how derivatives, again image derivatives, are being used for computing these corners. All right, so this is like a sample image, and again you can see that you have a different rotation, like in these two images it's the same object, and even like the viewpoint is different, the lighting condition is different. So if we run that Harris corner detector, this is the response you get. So this is like the response value C for each of the locations, and you can use a threshold. So you're just doing filtering, right? So these are your corners, and then you perform non-maximal suppression, because you can't have like a big region as corner, right? So you will get something like this. So these are all the corner points in your input image, and you can see that, I mean, it's kind of giving you a nice pattern, right? So even though like there was rotation, there was like differences in the illuminations, still they are kind of not exactly same, but they are consistent. So these are like the detected corners overlaid on the original image. Okay, so I understand we skipped a lot of details here, but that's fine. So just try to understand like what are the operations being performed at higher level, and I think that will be sufficient. So question from Kasun, what is that O operation? Okay, let me go back. Yeah, this is just multiplication. Ix and Iy, right? This one over here. All right. Now this is something interesting. So next topic, this is histogram of oriented gradients, and as the name suggests, like we are going to use all these terms. And this is not like key point detection, but this is actually like extracting features from your input image. Right, and this is I think a very effective way to extract features. Still people use it, and you will later see like it's a very straightforward algorithm. And so it will use like all the concepts we have learned so far. So that's a good thing. I think there's a question from Fernando. If we have multiple corners close together, then NMS will keep the sharpest corner. Yeah, that's correct, Fernando. So it's like analogous to when you have multiple pixels detected as an edge, right? But you only keep one of them because only one pixel can be edge, right? So it's a same idea. And again, this NMS, it's a very popular algorithm. It's not just used for edge detection or these key point detection. Later we will see like when we are doing object detection, even in that case we will use this non-maximal suppression. So it's a very general concept which is used like in most of the problems and most of the algorithms. Okay, so this is I think a very interesting algorithm, and we are going to cover this like in detail. And this I think you might get in your next programming assignment as well. So try to understand this very well, each and every detail, because you'll have to go back and implement this. So now let's first talk about edges, because this feature descriptor is going to make use of edges. And now let's say this is your input image, and you have seen that using simple derivatives and Gaussian smoothing, you can detect edges like this. Now, what histogram of gradient that HOG feature descriptor is trying to do is, it's trying to compute the statistics of the edges in any given image. Okay, for example, to give you an like a very high level idea, if you have a digit O, right? So then you will have certain type of edges in that particular digit as compared to a digit 1. So 1 might have all the edges which are vertical, and O might have very few edges which are vertical, and you will have like edges in all the directions. So it's kind of making use of that statistics. So if you just count the number of edges in any particular direction, you can easily differentiate between digit 0 and 1. So that's a very simple example, but that's the basic idea behind HOG. Okay, so I think the first work which proposed this HOG descriptor was this paper from Dalal. It's a very famous paper, very popular, and they used it for human detection. So if there's a person in any image, then you want to detect whether there's a person present or not. All right, so this was a data set which was used, and you can see that it's very difficult data set, like a lot of variations. So it's kind of person detection in the wild. All right. So let's try to go over some of the basics, which we have already covered in the course, but which we will require for understanding HOG. The first concept is histogram. And histogram is something, if let's say you have an image, what you do is you just try to find out what's the frequency of the intensity in the input image. All right. And by frequency, I mean like how many times a particular intensity is occurring in the input image. So if you look at this image, and this x-axis is representing the intensity, so it's going from 0 to 6, and you can see that we don't have any pixel which has intensity of 6, so 6 is almost blank. The y-axis is telling you the frequency of those intensities, right? How many times that intensity was present there in the input image. So if you look at 0, so we have a 0 here, 2, 3, 4, 5. So that's the frequency. So for 0, we get 5. Similarly, you can count the number of pixels which have intensity 1. So this is 3 and 6. All right. Similarly, 2, it's close to 5. We don't have any pixel with intensity 3, so it's 0. And similarly, you can count for 4 and 5. So this is called histogram of your intensities. All right. Is there a question? Okay, all right. Now, similarly, we can compute image histogram, right? So that was just image patch, but we can essentially do that for the full image. And this x-axis over here is the intensity value. So we can go from like very dark pixel to very, very bright pixel. So this is close to 0, and this is close to 255. And the y-axis is giving you number of pixels of that particular intensity. Okay, so this is like just a sample histogram for one random image, and here you can see that you have like a very nice distribution. So you can see that you have that many pixels with which are very dark actually. Okay, you have some gray pixels as well, and you have a lot of pixels which are brighter, but you don't have like super bright pixels. That's close to 0. Okay, so that's called a histogram. Now you know histogram and you have seen edges. Now let's see how we can compute histogram of oriented gradients. So we have an input image I. What we do is, for each pixel location, so ij is the location, right? We want to compute HOG feature, right? So we are computing HOG feature not for the entire image. First, we start with like just one location. So what we do is, okay, so we have total 5 steps. That's fine. We'll go over those. So what we do is we place a window or a block over this location. Okay, so that's the pixel ij, and this is the block. And again, you will see like this, as I said earlier, this sliding window and this using of blocks, it's very popular. You will see like in most of the algorithms, this concept is used. Okay, so you have this window. Now, okay, so that's the first step. And again, so this window will have some size depending upon like how many pixels you have this in window. That will be X and Y. The next step is, what we do is we divide that block into sub blocks, and we call these sub blocks cells. All right, so in this case we are dividing this block into 2 cross 2 grid, which means we'll have 4 different cells. Right, we can divide it into 3 cross 3 as well. That will give you 9 different cells. Okay, so again, so this is one parameter. So later we'll see that you have certain set of parameters which you can use when you extract the features. So this is one of them. The first parameter was what will be the size of this block. And then what we do is we compute the orientation histogram of each cell. All right. So orientation histogram is histogram, you know. Orientation histogram is like histogram of orientations. So orientations means like you will have edges in this particular cell, right? Then you're just computing histogram for those orientations. And we'll talk about that in detail. All right, so that will be the third step. The fourth step is you just take those histograms. So for each cell, you will get a histogram, right? Then you can just concatenate those histograms, which means that if one cell, the histogram for the first cell has a size, let's say 100, it will have 100 values. So after concatenation, these 4 cells will give you a feature vector of 400. So just concatenate. That's the first step. And I think we are almost done. The final step is fifth one. We just normalize that long concatenated feature vector. Right? And again, normalization, it's required because you might have different intensities in different images. Right? So, and there are different ways which you can use for normalization. The first option is you just divide that vector v. So this vector v is like that concatenated vector. So you just divide that with Euclidean norm. All right, so this is another application of norm. Someone was asking in the first lecture why we need norms. So you just divide that by a Euclidean norm. Or what you can do is you can just divide by L1 norm. So another application of norm. So this is just like you just add the absolute values. And if you want to be like more, you want to do more fancy stuff, what you can do is you can make it more complicated. But again, this is just normalization. It won't change like the performance a lot, maybe slightly. So you first divide using the Euclidean norm. All right. Then what we do is we try to cap the upper limit of the intensity. Okay. For example, if we set a threshold of zero point 0.2, so all the values which are over 0.2, we'll just make them 0.2. Right, and then we again renormalize. We again divide it with the Euclidean norm. And the reason to do this is sometimes your pixels might be very bright. They might have a very high intensity. So that will influence like what kind of histogram you're getting. So then you don't want to influence those kind of edges, or you can say like those kind of histograms to influence like the full feature vector, right? So that's why you need like this two-step normalization. And it's just kind of saying that if it's high, it's high. So if it's over 0.2, you just say it's high. You don't differentiate between 0.2 or 0.8 or 0.7. All right. So those are the only 5 steps which we need for histograms of oriented gradients. And as I said, it's a very simple algorithm, but very powerful. Now let's quickly go through like all those steps using this sample image. So let's say this is the input image. And first we start with the blocks. All right. So as I said, we at each pixel location, we will put this block, and this block will have some resolution. I think in this case, let's say we have a 16 cross 16, which means that 16 pixels in this height and 16 pixels in the width. That's parameter number 1. Okay, so each block consists of 2 cross 2 cells with size 8 cross 8. Okay, so then we are dividing that block into 2 cross 2 cell. So that's another parameter. We can change that as well. And when we are doing that, so since the original size of the block was 16 cross 16, so the size of each cell will be 8 cross 8. All right, because we are just dividing each dimension into half. So which means that each cell has 64 different pixels. So that's good. And then what we do is we put this block at all the possible locations, the way you were doing for your CNNs, right? Convolutional neural networks. You are just sliding your window. This is same. You're just sliding these blocks. And then for each location, you will collect that descriptor which we computed using the histogram of orientations. And to compute the descriptor for the whole image, you will just concatenate the descriptor for each block. So now you might have seen that, and that will be a very long feature vector, and that's true because this is kind of handcrafted feature. So this will be a huge vector, but that's how we extract histogram of gradients. So again, there are some parameters like how you slide your blocks. So in this case, the stride is kind of one cell, right? You're striding one cell at a time. You can also stride 2 cells at a time. Okay, so that's pretty simple. And now let's quickly look at, so one part which we haven't covered yet is like how we compute the histogram of the orientations. So that's really important. So given an image, you know how to compute partial derivative in X and Y direction. This is fine. And you know how to compute the gradient direction, right? You just use the tan inverse, and you also know how to compute the gradient. Now, once you have that, to compute the orientation, the histogram of the orientations. So that so remember, like that you do for each cell, right? Each cell in the block. Now, what you do is now you have computed the gradients, right? So these gradients are for each location. So if you have 64 different pixels in a cell, you will have 64 different orientations. Now, what you can do is you can create bins for those orientations. Let's say you are computing the orientation between 0 and 120, sorry, 180. Okay, so what you do is you first quantize the gradient orientations into multiple bins. In this case, we are dividing into 9 different bins. So these are like equidistant bins, and you can divide into 18 different bins, or maybe 36 different bins, 27 different bins. So that will only change like how many values you will have in your histogram. So let's say we divide into 9 different bins. So this part is pretty little bit tricky. So please interrupt me. Let me know if something is not clear. All right. So you have these angles and you have all these bins. Now what you do is you go to each cell, and as I said, in this case we'll have 64 different orientations. So for each pixel or each orientation, you just try to figure out, okay, which bin this orientation falls. For example, if let's say the orientation was 10 degrees, okay, so you can just see that 10 degrees is actually in the first bin. Then what you can do is you can take the magnitude of the edge, how strong that edge was in the direction of 10 degrees, and you will put that magnitude in the first bin over here. All right, so that's the vote for each bin. So the gradient magnitude, that's why we need the gradient magnitude, right? Not just the angle. So whatever we are adding to the bin, it's the gradient magnitude. Now 10 degrees is pretty simple because that's just the center of this bin, right? And similarly 30 will be pretty simple, straightforward. If you have an angle like of orientation of 30 degrees, you just take that magnitude and put in the second bin, and you keep doing that, and that will give you like how many pixels have orientation which fall in this particular bin or this particular bin. So that's exactly what we're computing. So at the end, this histogram is going to give you like a sense of like which was the most dominant edge in this particular cell. So there is a question from Amit. So here absolute value of theta is considered. Right. I mean, you can actually you can also compute the histogram from 0 to 360. That's also fine. All right. But yeah, you are right. If you're counting between 0 and 180, so we'll have to just consider the absolute value. Question from Momal. What is vote? Yeah, I think that's a good question, and that's actually tricky. Let me actually go back to make it more clear. All right. So if you remember, like when we were creating the histogram using this image patch, what we were doing is we are just counting the number of pixels which have this particular intensity, right? So number of pixels with 0 intensity, it's 5. So in this case, the vote is actually just 1. So whenever that value is present, you will use a vote of 1. Okay, so you found this, so you added 1. You found another 0, you added 1, right? So that's why you get 5. But you could use a different weight. Let's say you are using a weight using a vote of 2. So for each value you are adding 2, right? So in that case the value of this histogram will be 10 instead of 5, right? Because each pixel is voting twice. Now, so this is simple, but the case where we are counting the orientations, we are not exactly counting the orientations. We are looking at the orientation, that's fine, but we are looking at the magnitude of that edge, because that's really important, right? If there is an edge which is like of a very small magnitude, so that should not count as much as an edge which is having a very high magnitude, right? So that's why we are using the magnitude as a vote. So if you look carefully here, what this means is if a particular edge has a very high magnitude, it should influence the histogram more as compared to an edge which has a very low magnitude. Is that clear, Moman?
Yes, Professor. So in
Okay.
case if an orientation is falling in the first bin of 0 to 20,
Mhm.
and the magnitude, the gradient magnitude of that pixel is, let's say, 2. So
Mhm.
we multiply 20 by 2, and then we
No, no,
edit, like, how are we?
no, we just take two. We just take the magnitude.
But
We
we
are
are
just
quantizing
counting.
the orientation, no?
Right. Okay. So let me give you a very concrete example. Let's say your angle is 10 degrees, right? So 10 degrees is like in the first bin, and let's say that particular pixel has a magnitude of 100. So we will put a value of 100 in this first bin over here. So we already have 100. And let's say, so we are directly counting the magnitude. Let's say we have another pixel in the same cell with the same orientation, which is again 10 degrees. But in this particular case, the magnitude is only 10. So then the vote will be 10. So then this value becomes 110.
Right, that makes sense now. Thank you.
Okay. Okay, great. So, and that's like the very simple case when it's just falling at the center of the spin. The more complicated case is when it's not at the center, it's like maybe towards 20 or towards 0. So that is more tricky. Okay. So now let me go through that. So for example, let's consider this angle over here, 85 degrees. Right. So this is saying that one particular pixel, there is a pixel in a cell with orientation 85, and let's say the magnitude is 200. Okay, so magnitude, just forget about that right now. So we'll use that later when we populate the values on in these bins. But let's focus on 85. So 85 will be somewhere over here, right? And the center is 90, which means that it's not exactly lying at the center of this bin. So it should contribute to this bin, and it should also contribute to the next bin because it's closer to this bin as well, right? So that's the idea. If the orientation is just at the center, perfectly fine. But if it's not at the center, we use that orientation not just to populate this particular bin, we also populate the neighboring bin, which is the next closest. All right. And let's see how we do that. We simply use weights. We see that how close it is to current bin and how close it is to the next bin. So for case of 85, if we compute the distance of this orientation with the center of this bin, which is 90. So 90 is the sharp center, right? So that's 5 degrees, right? And if we compute the distance of 85 with the next bin, which is, you can see the center is 70, right? So that will be roughly 15. All right. So then what we do is we say that, okay, the next bin is 15 points away and this is 5 points away, which means that we should give higher weightage to the closer one. But you can't use like the directly the distance. But what you can do is you can use the distance from the other bin, right? So if it's far away, you can use that distance as a weight for the other bin. So for example, if it's 15 points away from 70, you can use 15 as a weight for this bin. So you just swap those weights or swap those values or swap those distances to use as weights. And that's exactly what we are showing here. So for 70, we are just using 1 over 5, which is like normalized value of like 5 degrees. And for the 90, we are using 3 over 4, which is like normalized value of 15. So if you look at 15 and 20, the total 15 and 5, right? The total is 20 degrees. So if you normalize 5, that should be 1 by 4th. And if you normalize 15, that will be 3 by 4. So then we use these as weights, and these weights will be used on the magnitude. So if the magnitude is, let's say, 200, so 3/4 of 200 will go into 90, and 1/4 of 200 will go into 70. I understand this is complicated. If there is any question, any doubt, please let me know.
Professor, why we have to do this? Why can't we use finer bins?
You can use finer bins, but what will happen is eventually your histogram will have like a lot of values, right? And we don't want that. We want to compress that.
Okay.
And even if you have finer bins, then I mean, so you are saying that you will have, let's say, uh, maybe if you are normalized, if you are just taking positive values, so you can have 180 different bins, right? So first of all, like 180 versus 9, so that's like a lot of difference, right, in terms of numbers you will have to save. But the other thing still remains, your orientation is not going to be perfect integer. It might give you 8.27. Then how far you want to go, right? Still you'll have to do some kind of voting or some kind of maybe rounding off. So there will
That makes
always be that trade-off.
Thank you. Yeah.
Well, why not just throw the entire value in the bin that like it belongs to? It's like why not throw 85 in the entire 80 to 100 bin?
Yeah, you can do that, but then you're losing some information, right? So let's say your orientation was 82. So if you just put all the magnitude in this bin, then you lost the information that that particular edge was also close to the next one, because 82 is not exactly at the center, right? It's so if you do this neighbor voting, then you are actually being more precise.
Right. Okay. Okay.
Sir, what about the negative degrees? Suppose a tan2 function returns values between -pi to pi, right? So how do we do that?
Yeah, so that was the question from Amir, right? So you can just use absolute values. So you can create 9 bins and go from 0 to 120. But if it's negative to positive, like pi, that's also fine. Then you will have 360 degrees. So again, you can have maybe 18 bins, or you can increase like the sampling rate here, right? You can have a bin of 40 degrees. But essentially, like whatever we are doing for 0 to 180, you can do for 0 to 360 as well.
Yeah, thank you.
Okay. So there's a question from Fernando. Basically a percentage contribution. Yeah, that's true. If angle is at exactly 80, then we contribute half and half. Yeah, that's true. So if the angle is at 80, it goes 50-50 because it's right at the center. So that's a good way to understand. All right. So any other question in this? If this is not clear, let me know. I can go over this again because I know this is complicated. But once you understand, you will see, okay, it was actually trivial. Because it's doing nothing. It's just looking at like how far away you are from one location. If you're close, it should be it should have high weightage. If it's far away, it should have less weightage, right? And since you only have like 2 points to compare with, you can just swap the distances to use as weights. It's that simple. All right, it seems there are no other questions. We can move forward. So that's it. That's what your that was a histogram of oriented gradients. Once you know how to do this for like each cell, then you take a block and concatenate all the histogram from all the 4 cells. So for example, if you have a discretization of 9, so each histogram will have 9 values, and then each block will have 36 values, right? 9 for 36, right? So each block will have 36 values, and depending upon how many blocks you have in the entire image, your feature vector will be of that length. And that's your histogram of oriented gradients. So just to summarize, like you need to have a block which you place over a pixel location, and then you divide that block into sub blocks. These are called cells. Then you compute orientation histogram. This is the, I think, the most critical step. And once you have that, then it's just like concatenation and normalization. So these are the only 5 steps in computing HOG. All right. So as I said, there are some parameters. First of all, like as you were asking me, why can't we go for why can't we also consider negative values? Of course you can quantize like from 0 to 360 degree, but one point to keep in mind is like, do you really want to differentiate between a vertical edge which is like going upwards and going downwards? essentially, I mean, it's the same thing, right? So having direction in your edges, sometimes it might be useful, but most of the times it won't be useful. You are just taking like twice as space. So keep that in mind. All right. So the other parameter is number of orientation bins you can use. So originally they use 9, but you can like use as many bins as you want. If you want to increase the preciseness or the accuracy of your histogram, you can increase the number of bins. That's perfectly fine. But if you don't care about like the fineness, you want very coarse histograms, you can just reduce the number of bins as well. So cell size is like how many pixels you have in each cell. So the standard is roughly 8 cross 8, so you have 64 pixels. And but you can also have like bigger cells. So the only difference will be like the neighborhood which you're using to compute your orientation or your oriented histogram, right? So that is something which is being controlled by your cell size. Again, block size is like how many pixels you have in your block. So if you have 16 cross 16, then that will, if you create 2 cross 2 cells, that will lead to 8 cross 8 pixels in each cell, right? So this is also fine. Okay, so for each block you will have 36 dimensions because you have 9 bins and you have 4 cells, so that gives you 36. Now this is a very nice visualization of HOG. So this is the input image, the astronaut, famous astronaut image. And if you look carefully, you can see that the edges are like, so this is not exactly HOG, but this is trying to visualize HOG. So for each cell, it's trying to display like the most dominant or like the top 2 dominant edges, right, which are present in that cell. And there you can see that therefore like the edges, those lines are actually aligning with the edges. And they are kind of showing you like what kind of edges are present. And if you don't look at this colored image, if you just look at this HOG visualization, I mean, you kind of can make sense like there's a woman present, right? And maybe a rocket in the back. So I think that's all I have for HOG. There's a question from Fernand. I think we covered that. So question from Amelia, does the cell size need to be a number that the block can be divisible by? That is, we cannot have a cell size 8 cross 8 if the block size is 18 cross 18. Yeah, that's true. That's a good point, Amelia. So your cell size should be like in a way that the number of pixels you have in your block, you should be able to equally divide like all those pixels into each of these cells. If it's not divisible, then it won't work out well, because you don't want like different number of pixels in your cells, right? Then your histogram, whatever histogram you're computing, they will not be normalized. So that's a good point. So I think that's all I have for HOG. And if there are any questions, let me know. The next thing we are going to talk about is SIFT features, which is also very interesting. It is a bit more complicated than HOG, but not as complicated as the Harris corner detector. So we'll cover that in the next lecture.
Hi, Professor. I have one question. So
Yeah, go
in
ahead.
step 3, we are computing the orientation histogram for each cell, and then we are going to concatenate those 4 cells into a block. So how exactly are we going to concatenate? What is the operation that we'll perform?
Okay, concatenate.
See,
Okay.
each cell will have its bin representation.
Right. So this is, yeah. Go ahead.
So each cell will have its bin representation, and from these bin representations, how do you just concatenate?
Okay. So for each cell, you will get such a histogram. That's correct, right? So what this histogram means is like you have just 9 different values, and each value is indicating like what's the total magnitude of that particular orientation. But essentially, these are just 9 numbers. So each cell is going to give you 9 numbers. You can just put them in a vector that will be like 9999, 36 different values.
Okay.
Right? So
That's
that's
how we
just
can.
36 dimensional feature vector. Yeah, that's how you can concatenate.
So the input for this algorithm is an image, and the output of this algorithm is just a feature vector.
Right, that's true.
And
It will be a feature
yeah.
vector.
And its size will be equals to, I mean, multiplied by width and height.
Yeah, so the total size of that feature will depend upon how big the image is. So that's one important factor. And like all the parameters which we are using, right? The number of cells, the cell size, the block size, the number of bins you have in your histogram. So all that will matter like in defining what will be the total width of your feature vector.
Thank you.
All right, so it seems there is no other question. If there is, please let me know, and we can end it here. Thank you.